In the previous videos, we talked about liquid nitrogen, cryogenic equipment, and the engineering principles behind these systems. Today, we're putting everything together. We'll build this complete cryogenic P&ID from scratch in AutoCAD Plant 3D, and more importantly, I'll explain the engineering decisions behind every major part of the system. At first glance, it looks like a simple vessel, but in reality, it's built as a double-wall tank. The inner vessel stores the liquid nitrogen, while the outer shell creates an insulated enclosure around it. The space between these two walls is evacuated to a high vacuum. Combined with multiple layers of insulation, this dramatically reduces heat transfer from the environment. Without this insulation, liquid nitrogen would continuously absorb heat, boil rapidly, and create large amounts of gaseous nitrogen. The entire purpose of this tank is to keep the product as cold as possible and minimize boil-off losses. With the storage tank complete, it's time to prepare one of the components we'll use throughout the entire drawing. Instead of inserting and configuring every manual valve individually, I'll create a reusable valve template. This keeps the workflow faster, the symbols consistent, and makes it much easier to build larger P&IDs. Now I'm adding the connections for the tricoque level indication system. Unlike electronic level transmitters, tricoques provide a simple manual way to verify the liquid level inside the tank. By opening each valve individually, the operator can determine whether liquid or gas is present at that elevation. In this design, A1 is positioned near the 95% filling level, while A2 corresponds to approximately 80%. Together, they provide a quick and reliable indication during filling operations. Next, I'm adding the pressure gauge connections. The upper connection is taken from the gas space above the liquid, while the lower connection is connected to the liquid phase. These two pressure taps can be connected to pressure instruments depending on the tank design and measurement requirements. These two nozzles are primarily used for differential pressure level measurement. The upper nozzle senses the gas pressure above the liquid, while the lower nozzle senses the pressure at the bottom of the tank. The difference between these two pressures is proportional to the liquid height, allowing the level inside the tank to be calculated continuously. Since both connections experience the same tank pressure, the differential pressure transmitter effectively measures only the hydrostatic pressure created by the liquid column. Next, I'm adding the two liquid withdrawal nozzles. The vacuum-insulated connection is typically used to supply liquid nitrogen directly to cryogenic applications, where minimizing heat leak is essential. The standard liquid withdrawal connection is commonly used to feed an external vaporizer, where the liquid nitrogen is intentionally converted into gas before entering the process. Next, I'm adding the gas withdrawal and gas return connections. The gas withdrawal nozzle is used whenever gaseous nitrogen needs to be supplied directly from the tank, without first vaporizing liquid nitrogen. The gas return connection serves a different purpose. It returns gaseous nitrogen back into the tank, typically as part of the pressure building system. As the return gas enters the vapor space, it helps maintain the required operating pressure inside the vessel. Together, these two connections allow the tank not only to supply nitrogen gas, but also to regulate its internal pressure during operation. Next, I'm adding the safety relief connection. Even with excellent vacuum insulation, some heat will always enter the tank, causing a small amount of liquid nitrogen to boil and increase the internal pressure. If that pressure rises above the design limit, the safety relief valve opens automatically and safely vents nitrogen gas to prevent overpressure. This is one of the most important safety features of any cryogenic storage tank. This tank provides both a top fill and a bottom fill connection. During top filling, liquid nitrogen enters the vapor space above the liquid level. The extremely cold liquid cools the nitrogen gas inside the tank, causing part of it to condense back into liquid. This helps reduce pressure rise during filling. Bottom filling, on the other hand, introduces liquid directly into the liquid phase. It minimizes turbulence and is typically used for normal filling operations once the tank is already cold. Next, I'm adding the pressure building unit connections. Unlike many other storage tanks, a cryogenic tank must actively maintain its operating pressure as liquid nitrogen is withdrawn. That's the purpose of the pressure building unit. Liquid nitrogen from the bottom of the tank goes to the pressure building unit. Inside the pressure building vaporizer, the liquid is warmed and converted into gaseous nitrogen. The gas then returns to the tank through the B nozzle, increasing the pressure in the vapor space and maintaining a stable operating pressure. Next, I'm adding the lower fill and drain connection. Under normal operation, this nozzle is rarely used. Its primary purpose is to completely drain the inner vessel during maintenance, inspection, or decommissioning. Having a dedicated drain connection allows the storage tank to be emptied safely without leaving liquid nitrogen trapped inside. At the heart of the pressure building unit is the pressure building regulator. This regulator continuously monitors the tank pressure. When the pressure drops below its set point, it opens automatically, allowing liquid nitrogen to flow through the pressure building vaporizer. As the liquid vaporizes, the resulting nitrogen gas returns to the tank, increasing the pressure back to the desired operating value. Next, I'm adding the product vaporizer feed line. This connection supplies liquid nitrogen from the storage tank to the external vaporizer. Inside the vaporizer, ambient heat converts the liquid into gaseous nitrogen before it is delivered to the process. Whenever the application requires nitrogen gas instead of liquid, this is the line that feeds the vaporizer. Next, I'm adding the Economizer line. As liquid nitrogen is stored, a small amount naturally boils off, increasing the pressure inside the tank. Instead of venting this gas to the atmosphere, the Economizer circuit makes use of it. When the tank pressure rises above the Economizer set point, gaseous nitrogen is supplied to the process first. This reduces unnecessary liquid consumption and helps bring the tank pressure back to its normal operating range. Once the pressure decreases, the system automatically returns to its normal operating mode. The evacuation port is used to create and maintain the vacuum insulation around the inner vessel. Without this vacuum, heat transfer would increase significantly, resulting in much higher boil-off losses. Unlike the other nozzles we've added so far, this connection is not used to transport liquid or gas nitrogen. Its purpose is to preserve the thermal insulation that makes a cryogenic storage tank so efficient. Next, I'll create a reusable pressure relief valve symbol. Since this valve appears multiple times throughout the P&ID, creating a template now will speed up the rest of the drawing and keep the symbols consistent. Now I'm completing the safety relief line by adding the pressure relief valves. These valves are one of the most critical safety devices in the entire cryogenic system. If the pressure inside the storage tank rises above the allowable limit, they automatically open and safely vent nitrogen gas, protecting the vessel from overpressure. Cryogenic storage tanks typically use 2 pressure relief valves with a changeover valve between them. This arrangement allows one relief valve to remain in service, while the other can be inspected, tested, or replaced without taking the tank out of operation. Next, I'm adding a thermal relief valve. Unlike the main tank relief valves, this valve protects an isolated section of piping. If both isolation valves are accidentally closed, liquid nitrogen can become trapped between them. As the trapped liquid absorbs heat, it expands and the pressure can rise rapidly. The thermal relief valve automatically releases this excess pressure, protecting the piping and equipment from damage. Next, I'm adding the drain valve for the fill connection. After the filling operation is complete, a small amount of liquid nitrogen can remain trapped inside the fill line. This valve allows the line to be safely depressurized and drained before disconnecting the transfer hose. In addition to the pressure relief valves, this system also includes a burst disc connected in parallel. Unlike a pressure relief valve, a burst disc is a one-time emergency device. Under normal operating conditions, it never opens. It is designed as the final layer of protection. If the pressure relief valves fail to protect the tank or the pressure continues to rise, the burst disc ruptures, preventing a catastrophic overpressure event. Our cryogenic P&ID is now complete, We've built the entire system, identified its main components, and understood the purpose behind each one. In the next video, we'll use this P&ID as the foundation for a complete 3D cryogenic model in AutoCAD Plant 3D, where the engineering workflow really begins. See you in the next one.